Hi guys, welcome back to my channel. Today we're going to be looking at complex numbers. But before we dive into this whole idea of complex numbers, I want to present to you this mathematical problem. And this comes from an Italian mathematician. Now I'm not sure if I'm going to say this name properly, Girolamo Cardano. And in 1545 he published this problem here. So if I was to take 5 plus square root of negative 15, and I was to multiply that by 5 minus the square root of negative 15, I get 40 as my answer. How can this be true when we can't find the square root of a negative number? So we've used the difference of two squares rule previously. So when we have the conjugate, so if I do a plus b multiplied by a minus b, I'm going to get the difference of two squares. So let's see how that rule applies here. So we've got the difference of two squares because we do have a conjugate, and so this is going to become 25 minus, now negative 15, the square root of that squared is going to be negative 15, and so indeed we do get our answer of 40. Okay, well let's test this out using a different method. Let's test this using the distributive law and see if we get the same result. 5 times 5 is 25. 5 times negative root neg 15 is going to be negative 5 root negative 15. Plus positive 5 root negative 15. And then again, we're going to have minus root negative 15 squared. So negative 5 root negative 15 plus 5 root negative 15, those two terms are going to 0. And then we have 25 minus, and again, the root of negative 15 squared is going to become negative 15. And so again, we end up with 40. So how is this possible? How do we find the solution to this particular question or this particular problem when we have numbers in here that don't actually exist? Well, what Cardano did not realize that he had stumbled upon at the time was he had stumbled upon this idea of complex numbers. So let's jump in and let's describe what a complex number actually is. Going back to our square roots here, we know that if we have 3 squared, that's going to be equal to 9. And similarly, if we have negative 3 squared, that's also going to be equal to 9. So if I want to take the square root of 9, I could have two answers. I could have positive 3 or I could have negative 3 as my solution. So what if I wanted to find the square root of negative 9, just like I wanted to try to find the square root of negative 15? Well, up until this point, we thought that we couldn't do it, but that's not actually true. And this is the really cool thing about mathematics. I think that people seem to forget that mathematics is a science, just like all the other sciences are, just like biology, chemistry, and physics. And maths is not something that we just learn or something that we just do. Maths is this sort of hidden language of the universe. And so there are still things that we're discovering mathematically to be true. So this is a really cool thing because when they first came up with this idea of complex numbers, we didn't actually have a use for it. They discovered this idea of complex numbers, and then now all these years later, we use it for things like looking at electricity or adapting power waves or, for example, using cell phone or wireless technology. But we didn't have all of those things back then. So how did this idea of complex numbers come about? Well, they came up with a really simple definition. So they've defined this imaginary number. So this number that doesn't actually exist. We've got all these applications for it, but it doesn't exist. And they call that imaginary number I. And we've defined this imaginary number I as I squared is equal to negative 1. So I, therefore, must be equal to the square root of negative 1. So we've defined this as an imaginary value or an imaginary number that does not exist. So let's go ahead and let's do some practice examples about how we use this number. Okay, so we're going to go through and we're going to determine the imaginary root of the following, and we're going to use our surd laws to do that. So when I have negative 16, that's the same as writing the square root of 16 times by the square root of negative 1. Now we've defined this as our value I. So the square root of 16 is going to be equal to 4, and the square root of negative 1 is I. So this is now an imaginary number or an imaginary value, but it's something that we can actually use. Let's do another example. So here I have the square root of negative 100. So again, I can factorize out my surd, and I can replace the square root of 100 with 10 and square root of -1 with I. One more example here. So this time we've got the square root of a fraction, so -25 over 64. So we can simplify this so that we have the square root of 25 over 64 multiplied by the square root of -1. Now, the square root of 25 over 64 is going to be 5 over 8, and the square root of -1 is I. So those are our imaginary roots for the following numbers. Let's use this information in a slightly different way now. Now, we know that I squared is equal to -1, so let's try and find the cube of I. Now, if we have I is equal to the square root of -1, I squared is going to be equal to the square root of -1 times the square root of -1, which is how we got -1. And then I cubed is going to be equal to square root of -1, square root of -1 times the square root of -1. Now, we already know that this is going to be equal to -1, and we know that this is going to be equal to I. So we can write this as -I. Okay, let's try it again now, except this time with I to the power of 4. Now, to simplify, we know that I squared is going to be equal to -1. And so if I do I to the power of 4, that's going to be equal to -1 squared, which is equal to +1. So this is a really cool feature of imaginary numbers, is that every fourth power is going to be equal to 1. So if I was to have I to the power of 8, for example, that's going to be equal to 1. If I had I to the power of 12, that's going to be equal to 1. If I have I to the power of 16, that's also going to be equal to 1. Let's try this last example. I'm going to rewrite this using I to the power of 6 as I to the power of 4 times I to the power of 2. Now, using that information before, I already know that anything with a positive power of 4 is going to be equal to +1. So really all I need to do is find this I squared. And we know I squared is equal to -1, so therefore this is going to be equal to -1. That's a pretty brief overview of how we can use these imaginary numbers to help us find square roots, and also how we can actually use that I value to different powers to find different values. So what is then a complex number? We've sort of alluded to the fact of the imaginary numbers, but a complex number is not just the imaginary component. Complex numbers have an imaginary component, as we've just seen, but they also have a real component. So usually we use the letter Z, sometimes W, to represent a complex number. Here I've got my value A, and that is the real component of my complex number. And here I have my imaginary component of my complex number. So for example, given the complex number Z is equal to 3 plus 2i, if I was to look at the real component would be equal to 3, and the imaginary component would be equal to 2i. So we can use that real and imaginary component to represent different things. So typically we use the real component of Z to represent the real part, which in this case is 3, and we use the imaginary component of Z, which is going to be equal to 2i. So let's go ahead and let's identify the real and imaginary components for each of the following complex numbers. So the real component is always going to go first. So in this case, the real component of my complex number is equal to 2, and the imaginary component of my complex number is equal to -4. Here we have a complex number where I only have the real component. So we don't have this additional I on the end here. So therefore, my real component here is going to be equal to 10, and my imaginary component is going to be equal to 0. Last question now, this should be C. So Z is equal to 9i. So again, in this case, we don't have the real component. So we could write this as Z is equal to 0 plus 9i. So this means that my real component of Z is equal to 0, and my imaginary component of Z is equal to 9. Alright guys, so that's just a very brief introduction into the world of complex numbers, how they came about and why we use them. And what we're going to look in the next video is we're going to have a look at some simple operations using these complex numbers. Alright guys, I'll see you in the next one.